Hi again guys. This is the second video in my two-part video on the proof of 3x3 magic squares. So we already proved that 5 goes in the middle. So I've already put that in the grid to get started, and that will really help us in proving the second part, which is that only even numbers go in the corners. So we're not going to prove that directly either. We're going to prove it indirectly by showing that no other odd number can go on the corners. So the odd numbers 1, 3, 7 and 9, we're going to show that they cannot go on any of the corners, which would imply that only even numbers go on the corners. So 5 is already there, as I say, so now we'll start with 1 and we'll show that 1 cannot go in a corner. So we'll put 1 into a corner, we'll put it in the top left corner, and if we do that, then that means 9 must go in the opposite corner. And if 9 goes in that opposite corner, then that means the numbers 6, 7 and 8 cannot go on the same line, because then we would break the rules, because if you put 6, then we're already at 15. If you put 7, then we've went over 15, and 8 over 15. So we can't put 6, 7 and 8 down in these two squares at the bottom, and we can't put 6, 7 and 8 in these two squares in the right hand column. So the numbers 6, 7 and 8 can only go in these two squares over here, the one below 1 and the one above 5. But that means we've got 3 numbers and we've only got 2 squares, which is impossible. So that won't work. So therefore, we conclude that 1 cannot go in a corner. And by symmetry, that implies 9 cannot go in a corner. So we don't even need to prove the case for 9, because we've proved it by symmetry. Because all we would need to do is put a 9 up there and a 1 down there. And then that applies to every corner, obviously, because all you would do is rotate the grid clockwise, anti-clockwise, flip it over horizontal, vertical, or diagonally, whatever. So one proves the other by symmetry. So now all we have left to do is to prove 3 and 7. But actually, similar to 1 and 9, if we can prove 3, then we automatically prove 7. If we prove 7, we automatically prove 3 through symmetry. So anyway, I'm going to put 3 up here. So that means 7 goes down there. So if 7 goes down there, then that means 9 cannot go on the bottom row, because if it did, then you would have 16. So let's try putting 9 in. You see, we've got 16, so we can't put 9 in the bottom row. And likewise, we can't put it in the right column, because then we've got 16 again, due to 7 being over there. So that means 9 can only go in one of 2 squares. It can go in the square below 3 or the square above 5. So let's try in the square above 5. If we put 9 in there, then we have a total of 12 on the top row, which means that remaining square must be a 3. But then look, we've used 3 twice, and we're not allowed to use numbers twice. And it's just going to happen over here by symmetry. If we put 9 here, then that would have to be a 3, and we're not allowed to use 3 twice. So that means 3 can't go in a corner. And by symmetry, we could have written it like this. And if you turn the grid clockwise, anti-clockwise, whatever way you want, you're going to get all the other situations where 3 is in a corner. So there you go. We've proved that 1, 3, 7 and 9 are not allowed to go into the corners. So that means 2, 4, 6 and 8 are the only numbers allowed in the corners. Therefore, only even numbers are allowed in the corners of a 3x3 magic square. So the facts that we know now, which we've proved, are that 5 goes in the middle and evens go in the corners. So thanks for watching guys, and I'll see you again soon.